Okay, let's get started. We have a lot to cover, and this is the agenda for today, basically. We're going to cover instruction set architectures, and we're going to cover LC-3 and MIPS assembly and programming. I assume everybody knows programming here, right? Yes, who knows programming? I hope everybody raises their hand. Who doesn't know programming? Okay, some people are raising their hands, but maybe they're joking with me at this point. Okay, but I'm going to give you a very low-level view of the programming. So we're going to program in machine code and assembly, and everything is built on top of it in the end. These are the required readings. Hopefully you're doing them. I think you'll learn a lot by doing them, and certainly it'll help the lectures. And next week's readings, please do them, because next week we're going to dive deep into the microarchitecture, how these instructions that we're going to talk about are actually implemented underneath. Okay, so recall this is the instruction cycle. Every instruction goes through this, and basically your computers are executing this loop of the instruction cycle whenever they do anything. Basically, they don't do anything outside of the loop, really, actually. You can consider everything as part of the loop that's going on. Okay, and we were talking about instruction set architectures. I actually gave you the slide. What is an instruction set architecture? It's really the contract between the hardware and software. It's essentially the manual that somebody defined as the contract. And that contract is different between different architectures. And what are the differences? The memory organization is different. The register set is different. The instruction set is different. The instruction set consists of multiple things, as we were discussing when we finished yesterday. So we were talking about opcodes, for example, and we finished the opcodes, actually. But just to jog your memory, opcodes are the part of the instruction that tells the machine what this instruction means, basically. What should the machine do? And this is in LC-3, it's very clean. It's these 4 bits at the top of the 16-bit instruction. And LC-3B, there are different instructions. And some of them are not used. If you get this opcode, for example, the machine ideally should really output an exception saying that, okay, I don't know what this instruction is. It's an illegal instruction because it's not defined, right? But all of the other instructions are defined over here. And this is the opcode in MIPS. It's not called opcode because opcode is somewhere else. When your opcode is 0, you look at this funct bits and they tell you what the instruction is. And you should get familiar with this very quickly because you're going to do some programming as part of your exercises also. Okay, that's the next slide. Okay, we stopped here. We were talking about data types. This is a second part of the instruction, set of instructions that are important. Basically, what kind of things do the instructions operate on? So bytes, words, they're data types for sure, but they're not very interesting data types maybe. But there are also other data types like 2's complement integers. Do you guys know what 2's complement integers are? Okay, good. Most people know. Well, if you don't know, basically these are positive and negative integers, and the way you take the negative of a number, of a binary, 2's complement binary value x, is you basically do a not on the x, which is the bitwise complement, and then add 1 to it. And if you don't believe me, do this for a bunch of numbers, and by induction you can prove that this works actually. Okay, for example, if you do the negative of 0, you not the 0, 0 is all zeros, not is all ones, right? And then add 1 to it, you get all zeros again, right? Of course, you ignore the carry. Okay, so this is how you do arithmetic using 2's complement integers in a binary machine. MIPS supports even more data types, and this is a data type. And this data type is supported in LC-3. And that's the only data type support aside from byte word, ... So MIPS supports 2's complement integers to do arithmetic. It also supports unsigned integers. Basically, you can interpret a 32-bit value as an unsigned integer. There's no sign, everything is positive or 0. So if you have all ones for a 32-bit value, that's basically 2 to the 32 minus 1, right? It's not interpreted as minus 1, which is the case in 2's complement integers. It's interpreted as 2 to the 32 minus 1. So that's a different data type. And there's also what's called floating point, which we're not going to get into. You can basically represent numbers like 1.3575. You can represent pi to some accuracy, for example. Okay, so trade-offs are involved, and let's talk about some of the trade-offs. Basically, what data type should be supported in the ISA and what data type should not be. This is really the ISA designer's decision, but this actually affects the high level. how the software actually takes advantage of it. For what's the benefit of having more or high-level data types in the ISA? What is the disadvantage? I'll quickly talk about this. Basically, think compiler versus programmer, and the programmer, I think of the compiler and the programmer the same, because they both generate code in the end. One is automated, one is human, or maybe some robot, versus the microarchitect. Microarchitect is designing the hardware, right? And this leads to the concept of semantic gap. So if you have data types that are very high level at the programmer level, then you have little gap between the programming language and the instruction set architecture. For example, in the programming language, you may have a hash table data structure, right? You all know about hash tables, hopefully. Linked lists, any kind of data structure. In the instruction set architecture, you may have that same data type also, a hash table somehow represented. Let's not go into how it's represented, but it could be represented as part of the instruction set architecture. And if you have that in your instruction set architecture, then the semantic gap between the programming language and the instruction set architecture is very small. The instruction set architecture is almost like the programming language that you have because it has a hash table construct in it. Now, this may be good because now the programmer wants to write a hash table. In assembly programming, you just say hash table, right? Or some way of expressing it. But then the instruction becomes more complex now because underlying instructions now cannot be just simple nots, ands, but they have to operate on a hash table. Okay, so basically this is a trade-off between the complexity of the difficulty of the job of the software or the compiler or the programmer versus the difficulty of the job of the hardware, the microarchitect. There are other issues related to this, which we're not going to get into. It affects performance in some way also, but I'm not going to get into that. So there was actually a lot of debate on this for a long time, and the debate is coming back again because we need more specialized languages to get high performance in architectures today, and how should those languages get translated to specialized architectures is a big issue today. So we're revisiting a lot of this discussion today. So ISAs may be changing in the future. For example, but there's a continuum here. For example, some very simple machines called RISC, reduced instruction set computers, they basically support only simple data types, very much similar to the LC-3, right? Only integer data type. On the other hand, very complex instruction set architectures support other data types like objects, very good for object-oriented programming. And they actually had permission checks, for example, integrated into the instruction set architecture. VAX architecture, which was very complex, supported doubly linked lists, for example, and various different types of queues for different operations. So we're not going to get into a lot of this, so you don't need to worry about that. But it's an interesting topic that's coming up again. For example, should matrices be data types? Maybe they should be, right? Especially given the prevalence of the matrix operations that we're doing today with machine learning. And some instruction set architectures had matrices as data types, but not the ones we're using today. Okay, so that's data types. There's also addressing modes, which I'm going to cover in a little bit more detail, because this exists a lot in the architectures that we're examining, and it's also important. But this basically is a mechanism for specifying where the operand of an instruction is located. How do you find the operand of an instruction? And we've seen already some addressing modes. I already told you a bunch of them. In LC3, there are 5 of them. Immediate or literal, constant. The operand is in some bits of the instruction, and we've seen that. If you remember the add immediate, we're going to see more of that. Register, the operand is one of the registers, general purpose registers, R0 to R7, and that's in the instruction encoding itself. You can get it directly from there and then access the register. And there are also memory. The operand is in memory, but then the question is, how do you calculate the address in memory? And LC3 has 3 different ways of calculating the address of the operand. One is PC relative, PC plus some offset. The other is indirect, and the other is Base+Offset, or register plus offset. We've actually seen PC relative and Base+Offset yesterday, but I'm going to go through this a little bit more. We haven't seen indirect. Indirect is very interesting. If you want to do indirection through memory, there's support in LC3 for that instruction. MIPS has many of these, not all of them, but it also has the pseudo-direct addressing mode, which is for jump and link, as we will see later. But it doesn't have the indirect addressing mode because it's too complicated for MIPS. It's actually interesting. It's a bit complicated for LC3. That's why it was removed from LC3B. Okay, so let's talk about operate instructions, and then we're going to go into instructions. That's going to be the first half of the lecture. There are 3 operate instructions in LC3. Not is a unary operation. there's one source operand. Unary means there's one source operand, and not is essentially the bitwise complement. Well, I said that already. Add and AND are binary operations. They have two source operands, and the add is 2's complement addition, but AND is a bitwise operation. In MIPS, there are many more because it's more expressive. LC-3 is very basic. And you know by now that if you have AND and NOT, you can do anything, right? Add is there for convenience, of course, right? Because you're functionally complete once you have AND and NOT. So in MIPS, there are many more. Most R-type instructions are binary operations, like add, AND, NOR, XOR, which is good. There are I-type versions of it, which basically operate on not 2 registers, but 1 register and 1 immediate operand, and then write the result into a register. And there are F-type operations, floating point operations that we're not going to go into. If you're interested, this is very interesting, but we don't have time, unfortunately. So let's take a look at NOT in LC-3. These are going to be very simple, so I'm going to go through relatively quickly. So if you have questions, you should shout. So basically, this is unary operation. It has 1 source operand and 1 destination, basically. And you see this, you can figure this out based on the manual that you have for LC-3, which is in the blue book. I don't have blue book. But how is this implemented in the data path? Basically, whenever you decode NOT in the decode stage, you jump into a state where ALU operation gets the right signals to do the NOT, basically. From the finite state machine where we decode, you get the NOT operation. And basically, the source register is specified to be the source register ID that's in the instruction, these bits. And the destination register is specified to be the destination register ID. And these bits don't matter, basically, for NOT. You don't interpret them when you're decoding NOT because they don't mean anything for NOT. And basically, what happens in the machine is you take the source register, do the bitwise complement, and write the result back into the register file. That's it. And if you have read Pat and Patel book, you will see this exact figure from over there. So there's one interesting choice in MIPS. There's no NOT in MIPS. You would expect NOT in MIPS. Do you guys know how you would implement a NOT in MIPS? Any guesses? Yes. You could do it with an AND, but then there's no NAND in MIPS also. But you could do it with a NOR. Right? There's a NOR in MIPS. So if we do this very quickly, I don't want to spend a lot of time on this, but this basically goes back to Boolean algebra, right? So if you want to compute NOT, that's NOT of x. You can write NOT of x as NOT of x and NOT of x. And the Morgan's rules tell you that that's the NOR of x, right? Essentially, you can use the Morgan's laws, and you can use all your Boolean algebra to implement something that doesn't exist. Basically, NOR of a source register with another source register, which is the same source register, is your NOT. Okay, so yeah, operate instructions. We're already familiar with actually some of these operate instructions. That's why I want to go quickly. But let's use the versions with 1 literal operand. We've seen the versions of these when you have 1 source register and another source register and do an add, for example, or an AND, and write the result to a destination register. Let's take a look at the ones with immediate operands. So for example, subtraction is another necessary operation. You do subtraction once in a while. Let's take a look at an example of how it's implemented in LC-3 and MIPS, because they're different. In MIPS, it's easy. But before we go into that, let's take a look at what do we have. In LC-3, we have the add and AND. It looks like this. Their format is very similar, actually. You have 1 source register and 1 immediate, basically 5 bits of immediate. And the operation specifies the add and AND. Add is that opcode. And the semantics says basically take the register value in source register 1, indicated by these 3 bits, and add to it this immediate 5 bits. But the register 1 has 16 bits, right? How do you add a 5-bit value to a 16-bit value? You need some more specification. If these 5 bits, remember the data type is 2's complement integer, you have some 5 bits over there. How do you extend them to become 16 bits? The idea is to sign extend them. Basically, if these 5 bits are negative in 2's complement, they should remain negative. So you extend you have 5 bits over here. The top bit is a 1. That means it's negative. If you want to sign extend that value to 16 bits, the remaining 11 bits at the top will be all 1s. If you want to sign extend a value that is positive or 0, which means that it has to start with a 0 at the most significant bit. You basically fill the top 11 values with all zeros. Makes sense, hopefully. You basically sign extended a 2's complement value. And that's the idea over here, so that you can add it to a 16-bit value that's in the register. Now you can basically encode an immediate to add to a register inside the instruction. But of course, the value that you can encode is very small, right? It's only 5 bits. And with 5 bits, you can only encode up to plus or minus 16, right? Is that correct? Should think about that probably. Because you need to go up to plus 15 actually, right? Plus or minus 15. Okay, anyway, we'll think about that. So AND is different, AND is bitwise. You basically do source register 1 and sign extended immediate 5. So basically you take the immediate and you sign extend it. So this is not, again, as I said, LC3B, all values are 2's complement. This is taken as a signed thing and then you sign extend it. Okay, you can study these in your reading. And clearly this is the source register, this is the destination register, and you have, I already said this basically. You need to sign extend this literal or immediate to 16 bits. So this is the assembly code of the add that we've seen. It's basically what this does is it adds -2 to the value in register 4, stores the result in R1. And this is how you do the machine code, as you know. And this is the machinery that you need in the machine to be able to do this. Basically, this is the instruction register. When this instruction is executing, you take the bottom 5 bits, sign extend them to 16 bits, and this basically shows exactly what's happening because it's a negative value on the top. You replicate all of the ones over here, so you get this value. And this is very interesting. This 1 says that you should take the value from the sign extended part and not from the register. That's why when you study the data path, you will see that. That's the difference between an add immediate and some other add. So you basically take this value, sign extend value, add to it the value you read from the register file from the source register specified by R4. And then once you do the addition, well, how do you know you need to do the addition? The decoder tells you that this is an add, and that add value is indicated, input as a control signal to the ALU. And the result of the addition, which you can check by doing this, by adding this value to this value, you will get this one. And the result of the addition is basically written into the destination register. Okay? So basically it's very simple. I've given you a little bit more complicated thing over here, which is this one. This one is cute, and you will figure that out when you read the book. Basically, this way you can quickly decide whether this bit 5 in the instruction decides whether you should take the immediate value as a second operand of the add operation, or whether you should take the value from a register. So if you go back to this slide, this 1 bit actually is important. If you go to the definition of add and AND, when you don't have an immediate, this will become 0, and you will have a register identifier over here, which will be interpreted as source register 2. And that's why that MUX works. So somebody who was designing the ISA was clever enough to make that so that you could quickly choose between a sign extended value, immediate value versus a register value. Okay, so in MIPS, it's very similar again. So I'm going to give you 2 examples, but it's going to be similar. We have I-type instructions that have 2 register operands and immediate. One is a source register and the other is destination register. And you have some operate on data movement instructions that look like this. But it's kind of very similar to LC3, except it doesn't have this single 1 bit over here. So they made a different choice over here. Here, the immediate is 16 bits because instructions are larger. You have 32 bits. You can afford 16 bits to be the immediate, and register sizes are larger, as you can see over here, and the opcode is larger. Okay, I've already said this. So this is the destination register in some instructions, it turns out, and source register in others. So there's this, it's not very nice, but you need to look at the definition of the instruction to see what RT, what these bits specify. Is it the destination register or is it the source register? That's why it's not called RS2 over here, because sometimes it's the source, sometimes it's the destination, depending on the opcode. And immediate is the literal or the immediate. So let's take a look at a similar example in MIPS. If you want to add value 5 to register S1, store the result in S0, that's how you would write the MIPS assembly. And that's what the field values look like. And MIPS also does a sign extension, basically. So you sign extend this, so you register S1 contains a 32-bit value. 2's complement, let's say, and immediate has a 16-bit value. What do? You sign extend it to 32 bits and add to the register and write the result into RT over here, and that's the machine code. Okay, so how do you do subtract? I've shown you add. In MIPS, there is a subtract instruction. Well, let's start with the high-level code we want to implement. You should be able to do the writing, conversion of this code to MIPS assembly, hopefully soon. But basically, this is one way of, this is a simple way of doing, implementing this high-level code in MIPS assembly. You basically add S0, S1, which happen to be B and C, store the result into a temporary register, T0, and then take that temporary register and subtract from it S2, which is D, and store the result into S3. So you have a nice subtract. That's nice. Well, LC3 isn't that nice. Same high-level code. The assembly looks like this because you don't have a subtract instruction, right? Well, you add R0 and R1, B and C, nice. But to be able to get minus D, you first need to negate it. And how do you negate it? You know that this is a 2's complement number. Let's assume that it's in R3. You basically first take the bitwise complement, not of it, and then add 1 to it. And that gives you the 2's complement of, that should be actually R3. That's a mistake, I think. Yes, 2's complement of whatever is in R3. Actually, it's not a mistake because I didn't define exactly where D is, right? It could be in R3 or R4, but this is not correct because I think the assembly, the destination is always on the left over here. So we should correct these slides. Okay, that makes sense, right? That's how you get the 2's complement. So there's a trade-off here. If you don't have a subtract instruction, now you need to add one more instruction. So you're executing one more instruction in the machine. Maybe it's slower, right? It's possible. But the control logic of this may be simpler because you don't have another instruction to decode, and you don't have another thing that you need to do in your ALU, right? Your ALU needs to be able to do sub. Okay. Okay, there's also subtract immediate in MIPS, which looks like this. So it makes life also easier. That way you can actually specify the immediate over here. So is sub-I really necessary in MIPS? It turns out it's really not necessary because if you're subtracting a small value, you're basically subtracting 3 from S0 over here. If you're subtracting that small value, you could do it with addition also, right? Because that small value fits in the immediate part. Okay? In LC3, you can do the same thing, basically. This is the add operation with an immediate. Okay, hopefully this is obvious, right? It's clean. Okay, so we're done with the operate instructions. Now let's take a look at data movement instructions and the addressing modes. We're going to look at different addressing modes now. So in LC3, there are 7 different data movement instructions. We're going to cover a bunch of them. The format looks like this. You have the opcode, you have the destination register or source register, and you have some address generation bits. These are how do you calculate the address? And there are 4 ways to interpret the address generation bits called the addressing modes. So PC relative mode, indirect mode, base+Offset, immediate mode. In MIPS, there are only base+Offset and immediate modes for the load store instructions. So MIPS is a little bit simpler in this case. So let's take a look at PC relative. We've seen this actually before yesterday. So if you want to do load and store, you basically have these 9 bits that are essentially the offset of the memory address that you're calculating from the program counter. So let's assume you're doing a load or store. There are different opcodes. Basically, you have the destination register. These 3 bits specify the destination register if you're doing a load instruction. They specify the source register if you're doing a store instruction. And this is the semantics of the instruction. Basically, the instruction says calculate the address to be program counter. That's the incremented program counter. Basically, the address of not this instruction, but the next instruction, plus the signed extended 9 bits. So you basically take these 9 bits and sign extend them to be 32 bits and add them to the PC and then access memory with that address and get the data at that location and move that data to the destination register. So hopefully this is clear. It's PC plus offset. It's also called PC relative addressing. Well, this is another one. This is basically, the store does exactly the same thing. The way it calculates this address is PC plus sign extended PC offset 9, except it doesn't read from memory. It writes to that memory address the contents of the source register specified over here. Okay, no surprises, simple. Okay, load in LC3. This is LC3 assembly and machine code over here. Basically, if you want to do a load in LC3, it looks like this. It's, again, very similar. So let's take a look at this. This is PC relative addressing again. So the idea over here is the load calculates its address by taking PC plus 1, which is the incremented PC. I don't show the PC over here. This is the incremented PC because we increment in the fetch stage, actually. You take that, you add to it, sign extended, bottom, I think in this case, it's 9 bits. Yeah, bottom 9 bits. Very similar to MIPS, actually. Bottom 9 bits, and basically do the add over here. And that gets you the, that gets you the address. You put that value into the memory address register. So this is the address calculation logic. Now memory address register got the address PC plus sign extended offset. And you need to read memory, wait until the memory finishes, and the memory will output the data into the MDR. And then the next cycle, you take the data in the MDR and put it into the destination register that's specified by the instruction. So you've seen something similar yesterday, so it shouldn't be a surprise. So clearly, in this case, the memory address is only plus 2 to the 9. I guess it's because it's a 2's complement. You have 9 bits. You can express the integers, 2's complement integers that are between 2 to the 8 and minus 2 to the 8 minus 1, right? Which are essentially 256 and minus 255. So that's your range that you can address in this case. So you can go only so far from this instruction. This instruction is at PC. You take PC plus 1, and you can go only 256 words high and 256 words lower. So, but the entire memory is, if you remember, it's 16-bit addressable. It's 2 to the 16, right? Clearly, you're not able to address the entire memory in this case. So this is an addressing mode that's not always useful. It's always useful if you know the offset of if you're close enough to the instruction, if the location that you want to load is close enough to the instruction in the layout, in the memory layout, and yeah, that's basically it. And you should know the address, of course. So there's a limitation. The PC relative addressing mode cannot address far away from the instruction. As a result, people have different addressing modes. Indirect addressing mode is the most complicated one. Well, we know the Base+Offset addressing mode, so I'm not covering that. We covered that already. Let's take a look at the indirect addressing mode. It's a bit more sophisticated. It looks like this. It looks very similar. Basically, you have the opcode, LDI, and STI, and the definition looks like this. So it's basically an indexed access. You first calculate the address as we did with load, PC plus sign extended, PC offset 9. Go to that memory location, take the 16-bit value. Now don't load that directly into the source register, but treat that value as an address and go to memory again. And now when you access memory with that address, get the value in that location and put it into the destination register. So that's the idea over here. You generate an address, go to memory, access memory, treat that location, treat that value in that memory location as an address again, and then go to memory again. So this is the LDI. Let's take a look at how this works. Again, you need exactly the same machinery. So you first calculate the address, incremented PC plus sign extended value. That's your address. You put the address into the memory address register, do the memory read, get the data into the memory data register, but now take that data and put it back into the memory address register, access memory again in the 4th step, and then once you get the data in the MDR, that's your data that you read. Make sense? So you're basically indexing. You're using the address of, you're using the data value in the first address you calculated as an address to go and access somewhere else. Now this is good because now the operand can be anywhere in the memory, right? Yes?
When I'm doing the first memory access and I get a new address that I want to look at, do I once again store it in the MAR, or can I potentially do process to go straight to the location?
Well, to be able to access memory, you have to put something into the MAR. So yes, you need to put it into the MAR. Yeah, there's an internal mechanism that needs to make sure that you don't. Basically, you need to be sure that you read the value before you destroy MAR. Okay, so this is interesting because now you can do indexed addresses. You can actually have a pointer or a memory address inside one location in memory and use that to access somewhere else. Okay, so Base+Offset, I've actually said that we've done it, but I'm going to go through it again. Basically, this is the Base+Offset addressing mode. This is hopefully relatively simple. You basically take the base register, sign extend the offset with the 6-bit offset in this case, because you have to encode the base register, and this has to be only 6 bits. And that's your address over here, and you access memory directly with that address and get the data value and put it into the destination register. So this is not indirect, as you can see. Once you calculate one address, you go to memory and get the data value. And store is the opposite, as we've seen. LDI is very interesting. Load indirect is very interesting because it enables indirection. So if you actually have, for example, an array of an array, for example, you can use that you can use LDI to calculate the address that you want to access in that array of an array, right? Okay. Okay, this is the assembly and machine code. Let's make it a bit boring because we're doing something similar, but I'll go through it so that you learn it fully. So basically, this is load register. That's why it's called LDR. You basically need to sign extend this immediate and add to it the base register. And base register in this case is 2. You do the addition, and that's your address. You put it into the memory address register. You wait for memory. That's the second step. Memory responds back. You get the data, and the data goes into the destination register. So it needs a different path over here to do the addition, as you can see. Okay, I've already said all of this. Okay, in this case, the address of the operand again can be anywhere in memory because you can put anything into this base register, right? Base register is 16 bits, memory address is 16 bits, so you could actually initialize a base register as you want. So in MIPS, LW, load word, and store word use the Base+Offset mode, but you actually knew that also. So if the high-level code looks like this, let's say you want to set the second element of an array to that variable A, you do this. Because remember, words are 4 bytes in MIPS. This is the base address of the array. You basically set the memory location at S0 plus 8 to S3, which is the value of A. And you can actually encode it this way. So immediate is the 16-bit offset that's sign extended to 32 bits over here. So we're going to look at an example program in MIPS and LC-3 relatively quickly again, because it's going to be simple. So this is a high-level code. Don't think about what it does. It has some meaning. Basically, you access the first element of array A, and you add to it some B that's coming, and then you subtract 5 from it, and then you store the result C into some other array. These are MIPS registers. So input registers in MIPS are usually indicated as source registers, S0, S1, S2. And MIPS assembly looks like this. Basically, you load the first element of array 0. This is the base address of the array, A, and add 0 to it, and load the result into T0. And then add T0 to S2, which is B, as we said, and store the result in T1, and subtract 5 from T1 by using the add immediate, store the result in T2, and store the word in T2 to the first element, first word of this array, which is starting at S1, and you add 0 to it because this index is 0. So hopefully this is obvious at this point. And LC-3 is very similar. I'm not going to go through this, but as you can see, it's very, very similar, actually. The syntax is different, and the register names are different, clearly, and some of the instruction names are also different, but load word is load register, store word is store register, and adds are indicated this way. You could have easily said this is add-I also right here. Is that clear? Okay, you can study this on your own. It's very simple. Okay, we'll talk about immediate addressing mode, which is a bit interesting. Actually, this is it's called an addressing mode, but you're not calculating the memory address in this case. You're calculating a value. It's called load effective address. It looks like this. Opcode should be 1110 in LC-3, and that's your destination register, clearly. So basically, what you're doing over here is you're loading the destination register with an addition, with something you calculate. You take program counter plus 1, that's the incremented PC, sign extend this 9-bit offset, and basically do that addition, and put that value to the destination register. So you don't go to memory in this case. You basically are creating an address based on the program counter for further use potentially. So the difference from the PC relative addressing mode is that you're not going to memory in this case. And you will, if you read the book, you will see why this is useful. Basically, instructions with PC relative mode access memory, but LEA does not. LEA just calculates an address with the PC and this offset, and then puts that into a register. That's why it's loading an effective address. Actually, load, I don't like the word load over here because it's not, load means that you're loading from memory, but this is really not loading from memory. So don't get confused. But all ISAs have idiosyncrasies like this. So this is LEA. Again, what it does is there's no memory access. That's why we don't have memory over here. You take the incremented PC and you sign extend this literal or immediate to 16 bits, do the addition, put the result into the destination register. And now you can use that as the base address of something, right? Now you can use that location value as the base register for a load instruction in the future. Okay, so in MIPS there's also something kind of similar, the LUI, load upper immediate. It loads a 16-bit immediate into the upper half of a register and sets the lower half to 0. So if you want to initialize a value, that's a great way to do it in MIPS. So it's used to assign 32-bit constants to a register. So high-level code, you want to assign this blah blah value for A. How do you do it in MIPS? Well, how do you construct this register, basically? First, you do load upper immediate. Basically, you load the 65E. What this does is, it basically takes this value, puts it into the top 16 bits of the register, and clears the bottom 16 bits to 0. So now you have the top half of the register, 65E, all zeros at the bottom. How do you put 4F3Z at the bottom? Well, you OR the register that you just created with the bottom values. Make sense? That's how you construct. Why could you not have constructed with a single instruction? Because you don't have enough bits to specify this 32-bit value. The instruction itself is 32 bits. You cannot put all of those 32 bits into the instruction clearly, otherwise you have no space for the opcode, right? Make sense? That's why you need 2 instructions to initialize a 32-bit value in MIPS. Okay, so this is an exercise, this is an addressing example that I'm not going to cover in full, really. But basically, you can have fun with what is the final value of R3 over here. Basically, if you start with this machine code, and if you have the ISA specification, you can clearly figure out what this is, right? You can basically figure out that these are these instructions, opcode. You can basically figure out that given this instruction, this is -3. Given this instruction, that's 14, ... And you can basically say what these instructions are. I actually showed you earlier. Basically, and then you can basically simulate what this does. This basically takes PC -3 and initialize R1 with that. That's R1. And then basically you simulate all of this. I would recommend that you go through this on your own. It's very simple. I don't think it's worth our time to go through this step by step over here. And we will see actually some other examples later on. So if you're given this machine code, and if you're given the specification of the instructions that contract, hardware-software contract, you can basically figure out what the program does. And this is actually in chapter 5.3.5. And the final value happens to be 5. So, okay, let me go into control flow instructions, and then I'm going to take a quick break so that your colleague can make an announcement. Clearly, control flow instructions allow a program to execute out of sequence, right? You have conditional branches and jumps, and we've seen the jumps. Conditional branches are used to make decisions. For example, the if-else statement. I said that before. In LC-3, there are 3 condition codes. Jumps are used to implement loops and function calls. They're not conditional branches. So for example, in LC-3, so jumps are unconditional. You have jump in LC-3 and J in MIPS. Let me see if I want to cover this. So okay, maybe it's a good time for you to make the announcement, but I will keep the break relatively short. Please be back by 12 past so that we can continue. Okay, so let's get started. So remember, we're starting a bit early. Later than I expected, but a bit early still. And we'll have more fun with the control flow instructions now. Okay, this is the slide I quickly covered. I'm going to cover it very quickly again, if I can. So basically, we want to allow the program to execute out of sequence so that we can make decisions in the program, if and else. in LC-3, condition codes are used. I'm going to explain what they are. Or we want to actually do unconditional jumps also, and we will see why you need them also, as well. Actually, if you want to do if and else, you need an unconditional jump. One of the jumps is conditional, the other jump is unconditional, so that you can avoid one parts of the code. And yeah, there are instructions for this. So what are condition codes? This is actually interesting. This actually exists in, for example, x86. In the most common architecture today, you have condition codes, and they're important to know. So each time you write to a register, general purpose register, the machine, LC3, automatically updates 3 bits. And these are single bit registers. They're called NZP condition codes. They're either set to 1 or cleared, set to 0. So if the written value, the value that you're writing to the general purpose register, whatever, R0, let's say, is negative, the machine automatically sets N to 1, Z to 0, P to 0, which means that this value is negative. If the written value is 0, the machine automatically sets Z. If the value is positive, the machine automatically sets P. Now you can make a decision based on these bits, right? Because you know what the last value that was written to a register was. Now you can branch on that value. If it's positive, you can do something. If it's negative, you can do something. If it's 0, you can do something. And you can combine. If it's positive or 0, you can jump somewhere. If it's negative, positive, or 0, you can jump somewhere. That's an unconditional jump, clearly, right? Okay, so x86 and Spark are examples of instructions, real instruction set architectures that use condition code. So let's take a look at one example of this, branch 0. So you're testing if the last value is 0, and you're going to take the branch, jump to some location if the last value was 0. It looks like this in assembly, and that's what it looks like, and expand it. Basically, these NZP bits, these 3 bits, specify which condition code this branch should test. What does that mean? If the branch tests one of the condition codes, and if that condition code is true, then you're going to change the program counter to program counter plus PC offset 9, as we will see. Basically, these 3 bits specify which instruction, the condition codes to be tested. The machine has the condition code stored in large NZP registers. And large NZP denotes the values of the corresponding condition codes. And you know what PC offset 9 is. Basically, the semantics of the instruction looks like this. If we are testing the N condition code, and if the N condition code in the machine is set, or if we're testing the P condition code and the P condition code in the machine is set, or if we're testing the Z condition code and the Z condition code is set, then PC gets PC plus sign extended PC offset 9. That's PC relative addressing mode for you. You jump into some other location in the program. And there are variations of this clearly by combining the condition codes. For example, BR, NP tests NNP condition codes. If either of them is true, then you branch. So if this condition evaluates to false, then you go to the next instruction. Right? So basically you're testing a value. If A is equal to 0, go somewhere, do the if statement, otherwise fall through. Makes sense, right? Okay, so that's the BR0. This is how it's implemented in the machine. This is the instruction register. You take the NZP bits out, assuming this is a branch instruction. And then you basically compare them to these NZP bits, which are essentially ANDs, 3 AND gates. And then if any of them evaluate to 1, then you branch. Right? You basically change the program counter to program counter plus 1, that's plus sign extended PC offset 9. Okay, and then you ensure that you ensure that this MUX multiplexer is controlled by this, right? If this says yes, you should take this value and put it into the program counter. If this says no, then the next value should not load the program counter, right? Because you've already incremented the program counter. Okay? Yes, very quickly.
Are the capital N's and P's fixed, or can they be defined for the program?
No, these are fixed basically. Whenever you write to a register, the machine automatically calculates whether the value is negative, 0, or positive, and it automatically sets those bits. Okay?
So I can set it.
You cannot set it explicitly. You have to do an operation. We can set it explicitly, but you have to go through writing to a register. Okay, so one question is, what if NZP are all 1? What does the machine do? Branch NZP? I already told you actually, yes? It's unconditional basically. You're testing all of the bits, And hopefully the written value is one of them, right? Otherwise you have a bug in the program. Because negative, 0, and positive cover all possible values in 2 complement integer. Yeah. What if n, z, p are all zeros? Yes? Exactly. Basically, it's a no-op. We call it a no operation. You go to the next instruction, basically. You may want to add those. So think about why you may want them. Okay, so branches in MIPS are similar, except they don't use condition codes. MIPS doesn't have condition codes. It has a different architecture. So basically, branch equal looks like this. Basically, this checks whether S0 is equal to S1. If that's true, then the PC is changed to a PC plus offset, sign extend offset again. That's the idea. It's very similar. And these are the source register, RS and RT. That's the opcode. That's the offset. And if RS is equal to RT, as I said, then PC gets PC plus sign extend offset. Of course, multiplied by 4 because you go to a word, right? And this is byte-addressable. And there are variations in MIPS, like branch greater than 0, for example, branch less than or equal to 0, branch not equal, and branch equal. Sounds good, right? So a MIPS assembly looks like this. LC-3 assembly looks like this. The equivalent to LC-3 assembly. So what is it doing? Basically, MIPS instruction is powerful. It's really comparing S0 to S1 and checking if they're equal. Whereas LC-3, you don't have such an instruction. It's not as powerful, but you can construct the equivalent of that instruction from multiple instructions. Well, what do you need to do? Basically, you want to compare one register to another register, to R1 to R0. That's what you do, basically. You first negate R1. That's the 2's complement of R1. The result is placed into R3. That's minus R1. And then you add minus R1 to R0. And the result is written into R4. Now, if the value in R4 is 0, that means that R1 and R0 are equal, right? And then you take the branch, if the 0 condition code is set, to offset. If the value is 0 over here, if R1 and R0 are equal, the condition code will be set to 0, and this branch is equivalent to this branch. Actually, this whole set of instructions is equivalent to this single instruction. So basically, you have a trade-off in the instruction set here. Do you have a powerful instruction, or do you have not so powerful instruction? It's a very similar trade-off. The same functionality requires clearly more instructions in LC3. And also the fact that you don't have a subtract adds one more instruction over here. But the control logic requires more complexity in MIPS. Now you actually need to orchestrate the fact that you're doing a comparison. And if it's 0, you need to do a 0 check over here. That 0 check happens automatically here to set the Z bit. But this instruction needs to do a lot more. Okay, so that's the end of 10A. So we covered a bunch of stuff, as you've seen. Hopefully this is clean and interesting. Any burning questions while I context switch to the other lecture?